Okay, g'day all. Welcome to another video. Today I was meant to be on C++, but I've actually made the Linux one, the Linux assembly video, so we'll go through that instead. And maybe get off my finger. Not you. Maybe have a look at C++ some other time. Anyway, we're almost on to Linux-specific things, and I think one of the big things that we've got to look at is jumping and branching. So let's just get stuck into it. I do want to say that there's a lot of theory in this video, and no practical work at all. So sorry about that in advance, but I really want to get through this stuff first before we get on to fun Linux kernel stuff. Anyway. The CPU usually executes instructions one after the other, but sometimes we want it to branch. We want it to jump to different points, maybe based on a condition, and sometimes we just want it to jump, on a condition or not. When the CPU can take one of two paths based on a condition, something like an if statement, it's often called a branch. Yeah. It's interesting to note that it's the RIP, the instruction pointer, the IP that points to the next instruction to execute in the CPU. Yeah, and it just moves through the instructions one after another, except when it comes to one of these branches or jumps. Okay, and it can jump to a label. No worries, which means it's just going to start executing instructions from the label instead of going one after another. We've actually used labels before in our code. They're pretty easy. They're just a way to name a spot in our code so that we don't have to deal with like relative memory addresses and that sort of thing. Yeah, so we can just have the head of a function called sum function, or we might have just a label, sum label, like that. Yeah, just a name with a colon. That's a label. They're even used for variables as well. Labels, good stuff. Okay, the first instruction of today, and we have 679 million instructions to get through, so just bear with me, but the first instruction today is jump, the unconditional jump. This is pretty useful. When the CPU reads this instruction, it immediately jumps to whatever the operand is. Yeah, so more often than not, the operand supplied here will be a label. Yeah, something like jump my label. Yeah, the CPU ought to find my label. It won't find it, but it'll know that it'll know where my label is in the code, and it'll jump there and start executing from there. Okay, and it's unconditional, so whenever the CPU sees this instruction, it takes the jump. Yeah, it's the same as BASIC's go-to command if you've ever programmed BASIC. There's three operand types. I think more than anything we tend to use the immediate operand type, but we don't do it explicitly. We just put a label there. But the assembler, I think, will translate to the immediate operand type. Yeah, so you say jump my label, and the assembler translates that to jump like -52 or whatever, however many bytes back my label is in the code. Anyway, thank goodness it does, because RIP relative addressing is a little tricky. Interesting, in assembly you can also jump to a register. So if you say something like jump RAX, it's going to jump to the absolute address that RAX is pointing to. Yeah, so you want to make sure that RAX is pointing to a label or some code somewhere to execute. But yeah, function pointers in assembly are really, really simple. Just a few examples of jump. Jump -8. You would never usually do that, but that does mean sub 8 bytes from the RIP. So start executing from 8 bytes previous to where the current IP is. Like I said, you don't usually do that. What you tend to do is jump my label. Yeah, something like this. Jump my label. You can add bytes to that, so if you want to jump to whatever instruction is 10 bytes ahead of my label, that's machine code bytes as well, so it's not easy to calculate this stuff. But you can, you can calculate the exact size of all the instructions if you get the program as references. Anyway, you can add little expressions to your label jump if you like. Not usually recommended, but you can if you want. What else have we got? Jump RAX. Yeah, like I said before, that's going to actually jump to wherever RAX is pointing to. Yeah, so you want to make sure that that's an executable segment somewhere. You don't just want to jump to your data segment and start executing that if it's not marked as executable. You'll just get a segmentation fault. Yeah, I think that's about all I wanted to say on the examples of jump. Alrighty, so let's just move on. This is where we start to get our 100 billion instructions. We're going to look first at the flags register, and This might come across as just a bit of an overwhelming amount of information, but like I said before, I just want to sort of skip through this really quickly so that we can get on to more fun things. Anyway, the most common bits in the flags register are flags. He's generally called in 64-bit mode. Your zero flag, your overflow flag, your sign flag, and your carry flag. Yeah, so there's a bunch more different flags, but we don't usually use them. And what happens is we often use the comp or compare instruction to set the flags in the register, in the flags register, and then after that we do what's called these conditional jumps, which we're just about to have a look at. The compare instruction takes two parameters and it subtracts the second from the first in Intel, so opposite in AT&T. Subtracts the first from the second. But the interesting thing about comp, and the useful thing, I suppose, is that it performs the subtraction, but it doesn't actually save the results to the first register. Yeah, so if you used a sub there, you'd get the same flags. The zero flag would be set up, the sign flag or whatever, but you'd also get the result saved in RAX. Yeah, so comp is a little bit different. It just compares the two values. Yeah, so you can have a register and an immediate value, or register and memory, or whatever you want really. Comp set up the flags register so you can do some conditional jumps. Here we go. Okay, so this is just a whole can of worms really. There's 169 billion trillion conditional jumps, and you can see them all down here. I mean, don't count, but I'm pretty sure that's how many there are. So on top of the unconditional jump instruction, JMP, we can also cause the RIP to jump based on the bits of the flags register. And this is what allows the CPU to do conditions like if statements and make loops like your for loops and all that sort of thing. They all come down to these conditional jumps. There's a bunch of other conditional instructions as well. Set instructions and conditional moves. The list of conditional jumps is pretty big, but they're not too hard, as we'll see in just a minute. And a lot of them are just different names for the same thing, so don't be worried about this big list down here. And a lot of them also you never ever use. Yeah. Or you rarely use, we'll say. Basically what's going to happen is if the condition is met, the condition that the jump's mnemonic implies, if the condition is met, then the RIP will jump to the label. Otherwise what it's going to do is called fall through, which means it's just going to keep executing instructions one after another. So it either takes the label jump or it just keeps executing as if it never saw the jump at all. One line after another. Okay, a little bit about the syntax for conditional jumps. You can basically only put a label there. You could put a number there if you want as well. But the point is you can't jump to a register like the jump instruction. The unconditional jump allows a register parameter, and you can't do that with conditional jumps at the moment. Alrighty, now onto the jumps themselves. So the zero flag indicates if the last instruction's result was 0. So if you, for instance, subtract one number from itself, like RAX has 1, RCX has 1, and you go something like sub RAX RCX, your result's going to be 0, and the 0 flag in the flags register will be set to 1. Okay, but that also happens to mean that the two operands were exactly the same. So if RAX and RCX have exactly the same values, then when you subtract them, you'll get 0 as the result. And if you remember that the compare instruction actually causes a sub in the background, that's why jump on 0 flag, which means jump if the 0 flag is 1, is exactly the same as instruction as jump if equal. So comp RCX RAX and jump if they're equal is the same as saying comp RCX RAX. I think I might have switched those around. Jump if 0 flag. Okay, and likewise jump if not 0 flag means jump if the 0 flag is 0. In other words, jump if they were not equal. Okay, so I hope that makes a bit of sense. 0 flag and equality are the same thing in x86. What have we got here? Joe and Jono. Joe and Jono, we'll call them. Jump on the overflow flag, or jump on not overflow. So often you'll just find that there's a couple of versions of these things. JO means jump if the overflow flag is set, and JNO means jump if the overflow flag is not set, or 0 in other words. The overflow flag usually indicates a signed overflow, whereas the carry flag indicates an unsigned overflow, as we'll see in just a minute. It means basically that the last result didn't fit into the signed destination operand without overflowing the signed value. Okay, JS and JNS is another set of signed flags. So we've got JS means jump if the signed flag is 1, and JNS jump if the signed flag is 0. So more often than not, the signed flag is set to whatever the signed bit was of the last result. So this is for signed arithmetic as well. The signed bit is just the leftmost bit of an integer. Okay, now on to some comparisons, and this is really where most of the jumps come from, these comparison jumps. So the CPU actually, this is pretty weird, but it doesn't actually know or care if we're doing signed or unsigned arithmetic. What it does is it sets the flags register to indicate the result of both, and then we, the programmer, reads the bits in the flags register and decides, what to do based on our data being signed or unsigned. So if you add one number to another, the CPU doesn't care if the numbers are signed or not. It doesn't care. It just cares that they're 32-bit integers, And then it's up to us to use either JB, jump below, or JL, jump if less. So it's these jumps here that we choose as programmers to use, which kind of decide whether we're treating our data as signed or unsigned. I suppose what I'm saying is that assembly is not type safe. The following are comparative jumps when the data is supposed to be unsigned. Okay. And the carry flag indicates an unsigned carry or borrow. Much like an unsigned overflow. And there's no real reason for this, but unsigned comparisons use below and above as mnemonics, whereas we'll see in just a minute that signed comparisons use less and greater. Okay, but these are unsigned down here. So JB, jump if below, which happens to be the same as JC, jump if the carry flag is 1. JNB, jump if not below. JAE, jump if above or equal. And JNC, jump if not carry flag. Oh, this is... You get used to them. Yeah, you get used to them. I tend to just pick one. And I would probably say JAE for this. Yeah, that would be my pick of those three. And JB for these first two. I use JB and JAE, jump if above or equal. But that's all it means. Yeah, it's not hard. Jump if above or equal, JAE. We've also got JBE, jump if below or equal, which happens to be exactly the same as JNA, jump if not above. Yeah, and that means that either of the carry flag or the Z flag are 1. It mightn't matter, but over here in brackets I've put, what actual flags these conditions read. Yeah, it might be interesting, so I've just put it in brackets. And the other one is JA, jump if above. Yeah, and this is talking in Intel syntax. This is talking about the first operand being above the second. We'll have a look in just a moment, but that's what it means. So if you're AT&T, it's the other way around. It means that the second operand is above the first. Yeah, that's what JA means. And jump below is, of course, the opposite. Anyway, along with unsigned comparisons, you're probably not surprised to know that we can also do signed comparison jumps. So when arithmetic is supposed to be signed, we tend to use these signed comparison jumps, and these often involve the overflow flag and the signed flag and the zero flag. The overflow flag and the signed flag are really just for signed, signed data. And what is this zero flag, since these indicate signed overflows? And yeah, that's good. Why did I... again, there's no real reason for this, and there's no real way to learn it either. You've just got to kind of, try and remember it. But greater and less are used for the mnemonics, as opposed to unsigned, which are above and below. Yeah, right here. So JL means jump if less. Yeah, or a synonym for that is jump if not greater or equal. If you're really keen on just typing out extra letters, you could do, that. It's pretty cool because it kind of looks like jungle, but I don't know. I would tend to use JL myself. Anyway, the JL, jump if less. JG, jump if greater. JGE, jump if greater or equal. And once again, remember that in Intel syntax, we're talking about the first operand being greater or equal to the second. Yeah, so the other way around in AT&T, the second being greater or equal to the first. Finally, the signed comparison, the last one here, JLE, jump if less or equal, which has the synonym jump if not greater. It's up to you which one you use. Yeah, I tend to use JL, JG, JGE, and JLE. Okay, we do have another few special jumps for the RCX. I'm not going to go through these, but yeah, you can do JCXZ, JECXZ if you want. And there's also a whole bunch of loops. Yeah, special jumps that deal with the RCX. You've also got the parity flag. It's not used very much nowadays, so we might just skip it. But it was for counting the bits in the lowest byte of the result, and determining if they're even or odd for error checking, I think. And the auxiliary carry, yeah. So this is another flag which has basically gone out of fashion, I suppose you'd say. We don't use BCD anymore, binary coded decimal. So yeah, auxiliary flag doesn't tend to come up. A little note about operand order. Yeah, this is what I was saying before. So comp EAX1, jump if greater to some label. That's going to jump if EAX is greater than 1, not the other way around. Yeah, do be careful. You've got to get that right, obviously. And AT&T is, you know, it's the other way around. So compl, CMPL long, and $1, it's an immediate value 1, and percent EAX. Yeah, that's going to jump if EAX is greater than 1, not the other way around. Okay. And the other thing to be aware of is that compare doesn't, or it's not always used, because the other instructions also set the flags, like sub sets the flags, add sets the flags, mul, you know, all of the Boolean operations set the flags. They all set the flags in some specific way, and sometimes they're a little unpredictable. I'm looking at you, Ink and Deek. So you've got to be careful, because some instructions, for one reason or another, don't set the flags the way that you'd expect. Ink and Deek don't set the carry flag. It's weird. I don't know. Ask Intel. Ask Intel, that's all I can say. But if you want to know for sure how an instruction sets the carry flags, sets the flags, sorry, not the carry flags, you just want to check out the Intel and AMD programmers manuals. I've gone completely crazy here. Oh, goodness me. Okay, yeah, so to finish up today, I'm not going to do any coding because I think this tute's far too long already. I wanted to just show a little bit of a comparison of how we do things in assembly versus C++ and or vice versa. So this first example just here, we got assembly on the left and C++ on the right. This is probably the most common assembly loop. Yeah, just a plain old loop. So my label is the label. That's the that's the head of the loop, I mean. And then we've got some code, which would be the body of the loop. It's just a comment at the moment. But then dec RCX jump not 0 to my label. That's very, very common in assembly. Yeah, and what you do at the top of that, you set up how many times you want the loop to run in RCX. So for instance, you might have mov RCX 100, and then this loop just here. What you mean by that is run this, you know, sum code 100 times. Here is exactly the same loop in C++. It's a little obscure, but I mean, it's pretty normal code, I guess. Yeah, so hopefully you can sort of line things up and kind of see why the assembly and the C++ are equivalent. But like I said, that's a very common assembly loop. It's not necessarily that common in C++. What you do tend to see in C++ is this next example. So this is probably the most common C++ loop. Yeah, the for loop. And I've put some colors over here to indicate pretty much the different sections in assembly versus C++. So the for int ECX equals 0 is probably this top line here. We set up our counter, which is ECX, to be 0. The next thing that assembly does is jump straight down here to the condition, which is at the loop tail. So CMP ECX 100, jump if it's less to loop head, which is basically this. ECX is less than 100. Yeah, so that's the red part of the for loop. After that, the assembly here will jump up here to loop head because of this JL just here, and you know, ECX is 0. We just set it up to 0, so comp ECX 100, ECX is definitely less than 100. Well, the IP will jump up here to loop head, which I think is probably equivalent to this open brace over here. Then it'll come down here to some code. This will be the body of your loop just here in yellow. Yeah, this is it over here in C++. And finally, once it's run the body of the loop, you've got your inc.cx and your loop tail. Yeah, I think those might actually be about, the other way round in... oh, it doesn't really matter. I mean, in C++, you don't actually execute the tail down here, the closed brace. But ECX++ and the bottom of the loop are there and there. Yeah, so I hope that makes a bit of sense. That's how you make a for loop in assembly. Like I said, this loop just up here is more common in assembly. Yeah, but you will also come across times when you want to use a for loop. So yeah, that's just one way to do it anyway. Okay, so this is the last little thing that I wanted to point out. Just how different assembly and C++ are. So what's normal for C++ is pretty weird for assembly, and vice versa generally. For instance, nested loops are really common with dealing with 2D data, and they're common in C++ and they're common in assembly as well, but we tend to write out completely different loops. A nested for loop is the common thing in C++, but in assembly we do a few strange things. So for one, we don't check that x is less than 100 straight after we've set it to 0. Yeah, so mov rcx 100, yeah, we want to run the loop at least once already. Whereas in C++, you set x to 0, then you check if it's less than 100. Like, that's what the for loop's going to do. It's going to say int x equals 0, is x less than 100. But in assembly, what we do is we say mov rcx 100, that's how many times we want the outer loop to run. Mov rdx 500, that's how many times we want the inner loop to run. Then we just run the body of the loop. Yeah, we don't do the check. Yeah, I hope that makes a bit of sense. But the other weird thing is that in assembly we count down often, and in C++ we count up. So for x equals 0, while x is less than 100, x plus plus. Whereas in assembly, what we're doing here is setting the counters to the last number, the 500 and the 100, and decrementing them, counting down. Yeah, it's pretty weird. It's pretty weird, but that's pretty normal nested loop in assembly. The other weird thing is that in C++ you'd be inclined to use those two variables, that x and y, for arithmetic in your sum code. And in assembly you could do the same. You could use the RCX and the RDX in some arithmetic in the body of your loop, but they are counting down, they're not counting up. So that mightn't be convenient. And what you might want to do is actually create different variables, so x and y, inside the body of your loop. Or probably in your data segment more than the more than the body of your loop. But you might actually create x and y variables, or use other registers for arithmetic. Okay, well, I hope that was an interesting little comparison there at the end. Don't get stuck in the habit of trying to write for loops in assembly all the time, or just trying to match what you do in C++ in assembly. They're very, very different languages, and this is basically nested for loops in assembly. I hope that was useful. Thanks for watching. See ya.